Today's topic is indirect search method for multivariate optimization problems. Now, let us consider a multivariate nonlinear programming problem, and we are considering the unconstrained optimization problem. That is why the problem can be stated as minimize f x, where x equal to capital X equal to x 1, x 2, x n, and these are the points in the nth dimensional space. Now, we need to solve this problem. I discussed about the direct search method. Today, my discussion will be on indirect search method. Now, unconstrained optimization problems are very much needed for some complex situation in engineering discipline, and also the unconstrained optimization problems are also very much important because important for the constraint optimization problem, because in the constraint optimization problem sometimes it is needed that we need to analyze the behavior of the objective function. In that case, the unconstrained optimization technique can give some idea about the movement of the objective function. That is why in general the unconstrained optimization problems are important in decision science. Now, if this is the problem for us, minimization of f x, and there is no only the maybe the for the decision variable the bounds may be given to us. Now, in this situation, now we need to just solve it. Generally, as we know, for locating minimum, as we have learned that the necessary and sufficient conditions we can use for it. As we know, the necessary condition would be del of f x divided by del x I, and as we know this value would be is equal to 0 if x star is the optimal solution. And through this necessary condition we are finding out the stationary points where the optimum may lie. After that we go for the sufficient condition, that is the second order derivative we need to do. That is del 2 f by del x I del x j, and we form the Jacobian for it, and we just see at the optimal point if the Jacobian value is positive definite, if this matrix is positive definite, then we say that the corresponding optimal solution x star is the minimum solution for the given unconstrained optimization problem. But the situation is not so simple always. For example, we are having one function f x, where f x is equal to x for x greater than equal to 0 and f x equal to minus x for x lesser than 0. For this problem, as we see, the function is not differentiable at the minimum point, because minimum of this function lies at the point x equal to 0, and at this point the function is not differentiable. That is why if we apply the necessary and sufficient condition in this situation, it will not work. That is why in general we are having different techniques for solving unconstrained optimization problems using the using the derivatives without using the derivatives. That is why the whole method we can categorize it into two parts. One is the direct search algorithms, which are non-gradient methods where we do not use the derivatives, or indirect search method, there that is the gradient methods, and there we are using the derivatives of the objective functional for the unconstrained optimization problem. Now, in the indirect search method, there is a very popular method is there, that is the steepest ascent or steepest descent method. This method is the very simple in understanding, and since this is the gradient method, it uses the gradient of the function at each and every, this is the iterative process. That is why each and every iteration this gradient this indirect search method, rather in specific steepest descent or ascent method, uses the gradient of the function at different points. Now, this steepest descent or ascent method, this is the generally the direct search method, since we do not use the derivatives, that is why these are all 0th order algorithm, and but the indirect search methods are either first order or second order algorithm, depending on involvement of the first or second order derivative in the process. Now, let me start with the simplest method, that is the steepest descent method, and that is for applicable for the minimization problem. Later on I will move to the more popular method, conjugate gradient method, Fletcher-Reeves method, etc. later on. That is why let me start my discussion with the steepest descent method, that is applicable for the unconstrained optimization problem, in specific the minimization. Let me just tell you the basic principle of the steepest descent method. As I said, this is the gradient method, this is the indirect search method. It uses the concept of gradient. As we know in vector analysis, gradient of a scalar function, and we know gradient of the scalar function if f x is the function for us, and if x is n dimensional points, then we can define the gradient of f x as del f, partial derivative of f with respect to x 1, partial derivative of f with respect to x 2, and in this way we get a tuple, and thus corresponds to gradient of the function, scalar function f. Now, as we know the gradient direction, if this is the surface of the function, gradient direction at any point would be the normal to this point, because this is the vector. Every vector is having the magnitude and the direction, that is why the gradient magnitude can be very easily we can get through the norm of this vector, but the direction of this gradient would be always in the at any point. If I just draw a tangent, then the gradient tangent plane in the surface, then the gradient would be in the normal direction. And we know gradient is the direction in which the function increases quickly. That is why if we just move from one point to the other point through the gradient direction, and since this is the optimization problem, we are always expecting the improvement of the functional value. That is why if we just move through the gradient direction very quickly, we can reach to the optimal solution. But since the problem is of minimization problem, that is why if we just move in the gradient direction, then the functional value, instead of decreasing, it will increase further. That is why what we do in the maximization problem, we use the gradient direction as for the movement of the respective iteration process, and but in the minimization problem we just consider the negative direction of the gradient as the best direction for improvement of the functional value. That is why this is the direction for the maximization problem, and we will just move through the negative direction in the minimization problem. This is at this point we will see the functional value, we will move to the next through this direction in the negative direction in the minimization problem, and with some step length we will reach to the another point, and this is the another level surface of the function, scalar function, and in this way we will just try to reach to the optimal solution. Now, in the process it is very clear, if we just discuss the minimization of the problem, it is very clear that if we just move in the negative to the gradient direction, the next question comes, how far should we walk? Shall we walk to the optimal solution directly? That means, is it that within one iteration we will reach to the optimal solution? That is not so really. That is why there is a concept of step length, there is a concept of direction in this indirect search method, and we will consider the corresponding step length and corresponding direction in each and every iteration. That is why my next discussion would be in specific the steepest descent method, where we will find out the optimal step length and the direction has already been fixed. For the steepest descent method, since this is the minimization problem, we are using the steepest descent method, we will move through the negative gradient direction, and we will use the steepest ascent method for maximization problem, and we will move through the positive direction of the gradient. That is why let me start the steepest descent process. We will start from a guess point, say this is the guess point for us, this is x naught, and from x naught we will move to the next point, that is x 1. What should be the point x 1? X 1 would be x naught plus lambda naught s naught. That means, in the first iteration we are considering lambda naught as the step length. That means, with this step we will move in the direction of s naught, and that is fixed here in the negative direction. That is why let me just in general, let me just give you the idea of the steepest descent method first, then I will come to the algorithm of the steepest descent method in the next. Now, what is the task for us? Let me just write it down. X 1 is equal to x naught plus lambda naught s naught. Now, my question is that how to find optimal step length lambda naught. Now, let me consider the ith step. That means, x 1 is moving to x 2, x 2 is moving to x 3. In this way, we are proceeding further and further. X 2 would be x 1 plus lambda 1 s 1. In this way, we are moving through to x I. X I would be x I plus 1 would be is equal to x I plus lambda I s I. Now, we are giving the general procedure to find out the optimal step length lambda I at ith step. Now, this is the position of the point x I. Now, we want to move to the next x I plus 1. We know S I is the negative gradient direction. At x I, that is why S I would be minus grad f at x is equal to x I. Now, for finding out lambda I, we will find out the functional value at point x I plus lambda I s I, and we will consider that point as the that value of lambda as optimal where it is equal to 0. Actually, we are finding out that lambda I which gives the minimum value for function at the point x I plus 1. That is why if we just write in this way, what we get in the next? We get, since there are n number of this is the point in n dimension, that is why we can just write in this way, summation j is equal to 0 to n minus 1 del f, let me start with 1 to n del f by del x j into del x j by del lambda I, and we will find out this value at point x is equal to x I plus 1, because we have considered the function at point x I plus 1, this is x I plus 1. Now, if we just consider del of x I plus 1 divided by lambda I, what is the value for this? This would be del of x I plus lambda I s I del of lambda I, that is why we will get this is equal to s I. If we just use this fact here, there are two terms. One term is the gradient of f, and this is another term, that is s I, because just now we got this value. We are considering at point x I plus 1, that is why we have considered the partial derivative with respect to lambda I at point x I plus 1. If this is so, from here directly we can write that grad of f at point x is equal to x I plus 1 t s I must be is equal to 0. All right. Now, let us consider a function a quadratic function, let me consider in this fashion, f x is equal to half x t a x plus b t x plus c. We may consider A as the positive definite and the symmetric matrix in this quadratic function. Then if this is so, then the function will be convex, and if the function is convex, then whatever optimal solution through the steepest descent method we will get, that would be the global optimal, because as we know through the Kuntaker condition, through the convex programming problem, that any convex objective function, if we just find out the optimal solution, that would be the corresponding global optimal instead of the local optimal. Now, if this is so, what is grad f? Grad f would be is equal to a x plus b. Now, if this is so, then whatever function we got previously, that is this one, let me just take the transpose of it, then we get SIT grad f x is equal to x I plus 1 equal to 0. Now, grad f at x equal to x I plus 1 means in place of x we will put x I plus 1. That is why let me just write it down, SIT grad f as x, sorry not here, x I plus 1 plus b is equal to 0. Now, what is x I plus 1? Just now we have seen x I plus 1 is the, we are considering after the ith step. That is why this is equal to x I lambda I s I. What is my intention? My objective is to find out the optimal value of lambda I, which minimizes the function f at point x I plus 1, and that is why we have taken the first order derivative with respect to lambda I. Now, let me just put the value of x I here itself, then we are getting a x I plus lambda I s I plus b is equal to 0, or if we just further simplify, then we are getting SIT a x I plus b. This is one part, and another part would be lambda I a s I equal to 0, and this value is equal to grad of f at point x I. That is why we, that is rather grad of f is equal to x plus b, and we are considering the steepest descent method, the direction that is the negative direction. That is why s can be considered as minus of grad f. That is why this is equal to minus of a x plus b, because we need this s value in this expression. Then here we are getting that SIT, this is the grad, this is the s value at point x I with the minus sign. That is why we can put it in this way, plus lambda is the constant and SIT a s I equal to 0. And what we get from here? We get from here lambda I is equal to SIT s divided by SIT a s I. That is why what we are getting here, we are getting that is the optimal value of lambda if we consider the negative gradient direction at point x I, that is my s I. If I just consider SIT s I divided by s I transpose a s I, this value, this is a constant value, A is the matrix of the given size, this if it is a quadratic 2 by 2 matrix would be there, then that would be constant, this is the constant, and this ratio can be considered at the ith level as the optimal step length. We will use this fact in the steepest descent method. We will use this lambda I star value in the steepest descent method. Let me consider this is as 1. That is why we can write down the algorithm in the next for the steepest descent method. here it's okay. Let me use the other page. Let me write down the algorithm for the steepest descent method. Step 1 would be start with a guess point x naught. This is the iterative process, that is why as I said we will start from x naught, we will move to x 1 with the step length lambda 1 star, then we will go to the x 2 with the step length lambda 2 star, and at each point we will consider the negative direction as SI, because this is the minimization problem. That is why let me write down the first step as a start with the initial guess point, and that is more important. If the starting point is far from the optimal point, then the number of iterations would be more. That is why starting point selection is very important for the iterative process, as we know. Start with the initial starting point, guess point x naught, certainly this is in Rn. Then we will move through to the next step, we will find out the gradient of the function at point x naught, and we will consider S naught as the negative of the gradient direction. That is why we will, let me start the iteration V I is equal to 1. Then we will find the surge direction. At I is equal to 1, we will just increase the value of I in the respective case and find the surge direction at I as minus of grad f at point x is equal to x I. This is for the minimization problem. Let me write down the algorithm for the general nonlinear unconstrained optimization, and grad f at x equal to x I. This is for the maximization problem. Now, once we are getting SI, our next task is to find out the next point from x naught to x 1. That is why we know S 1, we want the lambda 1. That is why we will find out lambda 1 lambda I star is equal to, from the equation 1, SIT SI divided by SIT A SI. Next, step 4, find out the next point x I plus 1, formulate new approximation for the optimal solution. X I plus 1 is equal to x I plus lambda I star S I. Then step 5, check for optimality. There are certain procedure for checking optimality of the new point. Check whether stop, otherwise go to step 2 with the consideration I is equal to I plus 1. This is a whole algorithm for us. Let us use this algorithm for problem for solving unconstrained nonlinear programming problem. Let let us consider one problem, minimization problem. Minimize f x1 x2 is equal to 2 x1 square plus 2 x1 x2 plus 2 x2 square plus x1 minus x2. Now, it is given that consider the starting point as 0 0. We do not know whether the optimal lies, that is why let me start with the most conventional point, that is 0 0 point. Then I am moving to next step. Here certainly x 0, that is the initial starting point, is 0 0. What is grad f here? That is the gradient value of this function. This is equal to 4 x 1 plus 2 x 2 plus 1, because we are considering this one, the function, the partial derivative of f with respect to x 1. What about with respect to x 2? It would be 2 x 1 plus 4 x 2. Oh sorry, we are not considering x 1 here, 2 x 2 square here, only we are considering x 2 square, 2 x 2 minus 1. Now, then what would be S naught? S naught would be negative gradient direction at point x is equal to S naught. That is why if this is so, just put 0 0 in this value, then we will get S naught as grad f at x equal to x naught would be is equal to 1 minus 1. That is why S naught would be negative to that minus 1 1. Now, we will move to the next, that is x 1 point from x 0, and with this consideration lambda 0 star S naught. How to find lambda 0 star? As we have just learned that the lambda 0 star would be is equal to S 0 t S 0 divided by S 0 t a S 0. Now, let me consider a few things here. That is here a is equal to, if we consider the function f x in the form of half of, this is the quadratic function, half of x t a x b x plus c. If this is so, then a would be is equal to 4 2 2 2. This matrix is the symmetric matrix, and corresponding b would be is equal to 1 minus 1. Then we will use this fact here. Therefore, A 0 t would be is equal to minus 1 1 minus 1 1 divided by minus 1 1 4 2 2 2 and S naught again. If we just get this value, we are getting it as 1 plus 1 2. This is equal to minus 4 plus 2 minus 2 0, and this is minus 1 1. That is why we are getting the lambda naught star value as equal to 1. Once we are getting it, we are getting x 1. What is my x 1? X 1 would be 0 0 plus 1 into 1 minus 1. That is why this is equal to 1 minus 1. This is my next approximation. I do not know how many iterations I need to reach to the optimal solution. We can check whether at this point the function is optimum or not. How to check it? Now, there are few criteria for checking optimality, but one of the most popular criteria is that we will just find out the grad f value at point x is equal to x 1. Now, grad f at point x equal to x 1, if I just put this is 4 minus 2 and this the whole value is coming 3 and something, that means it is not equal to 0. If this is not equal to 0, then minus grad f will not be again 0. Then what is the implication of this? It implies that there is a possibility for further improvement of the functional value. If we see at any point, if in the process of iteration the grad f function is coming 0, that means we have to stop the iterations there itself, because there is no possibility to proceed further, because functional value will not increase further if I just move. Now, x 1 we got, that is why let us move to the next point, that is my x 2. What is x 2 again? X 2 would be is equal to x 1 plus lambda 1 star s 1. First of all, we need to find out s 1. What is s 1? S 1 is the grad f at point minus of grad f at point x is equal to x 1. Now, just now we got the grad f value, and that is 4 x 1 plus 2 x 2 plus 1, that is why 4 x 1 plus 2 x 2 plus 1, and here it is coming 2 x 1 plus 2 x 2 minus 1. If I just move at the, if I just write down at x is equal to 1 minus 1, then this value will come as 4 minus 2, that is 2 plus 1. Now, we are considering x 1 as equal to x naught plus lambda 1 into s 1. I am sorry, x 1 is equal to lambda x naught plus lambda naught into s naught. Lambda naught is lambda naught star is coming 1. What about s naught? S naught is coming minus 1 plus 1, that is why it is coming minus 1 plus 1. That is my next s 1. If I consider s 1, here x 1 is equal to minus 1 plus 1. If this is so, x equal to minus 1 plus 1, when in the next point would be x 2 point. X 2 point would be is equal to x 1 plus lambda 1 star into s 1. Now, we need to find out the value of s 1 here, and for finding out the value of s 1, that is the negative gradient direction at point x equal to x 1. That is why this is the gradient value at x equal to x 1 minus 1 plus 1, we get the value as minus 4 plus 3, that is minus 1, and this is again minus 1. Then once we are getting s 1, what about lambda 1 star? Lambda 1 star would be s 1 t s 1 divided by s 1 t a s 1. If I just write down the value here, a value would be 4 2 2 2. This we are getting from the objective function minus 1 minus 1. Oh, one thing should be mentioned here, this is minus of grad f, that is why this is plus 1. Plus 1 plus 1. If we get it, that would be 2 here, and here it would be 6, 4, 1, 1. That is why it is coming as 2 divided by 10 equal to 1 by 5. Once we are getting lambda 1 star, then from here we can get x 2 as x 1, that is minus 1 1, lambda 1 star, that is 1 by 5, and next is my s 1. S 1 we are getting it as plus 1 plus 1, and it is coming minus 4.5, 4 by 5 and 6 by 5. This is my x 2. What I will do in the next, again I will move to x 3. X 3 would be is equal to x 2 plus lambda 2 s 2, and again we will find out s 2 first. Once we get s 2, we will get lambda 2. In this way we will proceed. If I just write down the entire value together, then we see we need 8 iterations to just reach to the optimal solution. Now, this is the first that I have just now solved. We are reaching to x 1 minus 1 1, that is my x 1, and these are all the gradient value, that is negative gradient value corresponding lambda I, and the next point that is equal to x I plus lambda I into s I. This is my x 2. X 2 is coming minus 4 by 5, 6 by 5 just now we got, that is why it is minus 0.8 and 1.2. In this way we are moving again through the gradient, negative gradient corresponding lambda I. If I just proceed the whole thing, what are the things we can observe from this table, that if we just look at the x I values here, as we see that almost we are coming to 0.9 for the last 3 iterations. In the first case we are getting 0.9 minus 0.91, in the second minus 0.97, in the third we are getting the last one, rather last but one, and the previous to that minus 0.99. That is why we should have some process through which we can check that where we can stop our iteration. There are 3 alternative methods are there, we can adopt any one of that. We will see that the functional value in the step and the previous to that point, and if we just see the ratio is very small, then we can stop our iteration. This is one process. Second process is that we will just see the gradient of the function at point x is equal to last one, say x I. If we see the gradient value is very small, if it is 0, that is nice enough, we should stop the process, but even it is very small, very near to close to 0, then also we can stop the process, because we can see that there is no possibility for further improvement. And there is another third process is also there, that is we will see the x I value, if they are very close, then also we can do. Actually we are considering here the norm of delta f, because delta f is a vector. If we see the norm of that value is coming very small, then only we stop. And here we can see that after the 8th step, the functional value at point x is equal to, as we know, at point minus 1 and 1.5, this gradient value is 0. That is why this is almost minus 1 and this is 1.5. Thus, we are stopping our iterative process. Now, this is one 2-dimensional problem we considered. Let me just move through to the 3-dimensional problem. The same steepest descent method we will use there. The example we are considering, minimize f x 1, x 2, x 3 is equal to x 1 square plus x 1 into 1 minus x 2 plus x 2 square minus x 2 x 3 plus x 3 square plus x 3. Now, it is written that start with x naught is equal to 0, 0, 0. Let us apply the process here. as we see that if we use that process where we have used the matrix A in the quadratic problem, but here to construct the matrix is very difficult. That is why if we just adopt that process for lambda, that lambda I star is equal to SI divided by SI ASI. SI is very easy to get, but getting A would be difficult here for 3-dimensional problem. That is why I will show you how to handle this problem in a different way. Now, let me start the process. What we want? We want that x naught should move to x1, and where x1 would be is equal to x naught plus lambda naught s naught. That is why let us first find out the grad of function f. This would be is equal to del f by del x1, del f by del x2, del f by del x3, and this would be 2 x1 minus x2 this is there is 1 x1 plus 1, and del f by del x2, that would be is equal to minus x1 plus 2 x2 minus x3, partially differentiating f with respect to x2. Then the next point would be with respect to x3, it would be minus x1 plus 2 x3 plus 1. All right. No, there is a term that is minus x1 x3 must be there, then only it will work. X1 square 2 x1 minus x2 plus 1 minus x1 plus 2 x2 minus x3 minus x1 plus 2 x3 plus 1. Sorry, this is this should not be here, all right, and it should be minus x1 only. Yeah, if this is the grad f function, then let us move to x naught. X naught is equal to minus grad f at point x is equal to x naught. If this is so, we are getting from here x naught is 0 0 0, that is why it should be minus 1 0, and here it would be minus 1. Now, once we get S naught, as we learned previously, we should get lambda naught is equal to S naught t S naught divided by S naught t A S naught. But here finding out A would be very difficult. That is why we will not use this process. What we will do? We will find out the functional value at point x 1, that is f of x naught plus lambda naught S naught, that is equal to f of minus lambda naught 0 minus lambda naught, and we will find out that df of that at point x naught must be is equal to 0. If we just equate, that was my basic principle for the steepest descent method. We have adopted that thing in our algorithm. If this is so, then we are getting the value as equal to 2 lambda naught square minus 2 lambda naught equal to 0, and this gives me the value for lambda naught is equal to half. Once we get lambda naught equal to half, then we will go to x 1. X 1 would be is equal to x naught plus lambda naught S naught, that is 0 0 0 half, and S naught would be minus 1 0 minus 1. That is why my point would be minus half, 0, minus half. This is my x 1. And if I just apply the same technique in the next, what we get? We get the x 2 value. That is why we have started with x naught, that was 0, 0, 0, moving to x 1, that is minus 0.5, 0, 0.5. If we apply the same process here, we will get x 2, and that would be minus 0.5, minus 0.5, minus 0.5, and proceed further. X 3 would be is equal to minus 3 by 4, minus half, minus 3 by 4, x 4 would be is equal to minus 9 by 8, minus 3 by 4, and x 5. This is the last point of iteration. This value is coming minus 1091 divided by 1168, here minus 66 by 73, and here minus 1091 divided by 1168. And as I said that I will just find out the either the functional value difference in the functional values at point x 5 and x 4. We will compare it. If we see the change is very small, our rate of change is very small, we can stop our process. But here we could see that grad f at x equal to x 5, if we just calculate, we are getting this value 21 by 548, 35 by 584, 21 by 584, and norm of this value at x equal to x 5, norm is equal to root over this one this value is coming 0.0786. We may consider as a small, this is a very small value. That is why we can stop our iteration at this point, and we can declare that x 5 is the optimal solution for this optimization problem. Now, that is all about the steepest descent method, but if we just discuss the indirect search method in general, and that there we see that steepest descent method is the most popular method because it is very easy to calculate the entire process, but there is another very popular method is there, that is called the congruent gradient method, and we are moving to that point, that method in the next. Now, one thing must be said that if we see that in the steepest descent method, if we see that the gradient of the function we are calculating, before going to the congruence gradient, let me just discuss this thing also. Grad f we are considering as a partial derivative, but it is not always so easy to find out the partial derivatives of the function, because if the function is discontinuous, in that case it is not easy to calculate the partial derivative of the function at point x I. In that case, what we do, we may use the difference, finite difference method to estimate the value for the partial derivative of f with respect to x I. How we do it? We are considering f of x m plus delta x I e y minus f of x m divided by delta x I. And what is the meaning of it? We are considering the function partial derivative of function with respect to x I. Now, if this is so, at point x is equal to x m, we want to find out the gradient of the function. Then what we will do? We will just change only the value for x I with a small increment delta x I u I. Now, the small increment is delta x I, and what is u I? U I is the direction. In the x I direction, that is the unit vector we are considering. That is why delta x I u I, if I just consider, let me take one example for this, then it would be very easy for us to understand. Say f x 1 x 2 is equal to, we are having 2 x 1 square plus 2 x 1 x 2 plus x 2. Now, we want to find out grad f at point x is equal to say x 1. X 1 is equal to some point we are having, let me consider it at 2 1, alright. Then what we will do? We will take the functional value at this point, 2 into 2 square, no, not 2 square, we will consider 2 plus delta x 1, some increment over x 1, plus 2 into 2 plus delta x 1. Instead of 2, we are substituting 2 plus delta x 1 into x 2 plus x 2. This is the functional value at point 2 1 delta x 1 0. Clear? X 2 is here 1, it is also 1, minus functional value, that is f at point x 1 itself. That is why we will consider f at 2 1 divided by delta x 1. If we consider this difference and the ratio, this corresponds to the function, this corresponds to the gradient of f at point x 1, and this process can be adopted by without using the differentiation of the function itself. Now, this is one process. This process can also be further be improved by using the central difference method later on, but this is the case for the steepest descent method. In the next, we will move to the conjugate gradient method, and we are getting better result with lesser number of steps in the conjugate gradient method. That is all for today. Thank you.